Hello, this is Dean Waldo from PLU. This is a short screencast to supplement the PChem lab for the iodine UV-Vis spectrum. So what I'd like to emphasize first is that in the lab we're making a measurement of the UV-Vis spectrum, and we'll be backing out information about the ground and excited state electronic potential. So one way to model that, as we saw in the handout from Gerlach et al., is that it can be modeled by a curve that looks something like the blue one here, and we're going to call that a Morse potential. And from the data you get in the lab, you'll be able to calculate things related to that Morse potential. But it's also interesting to try to do a quantum mechanical calculation to calculate that same thing. So what we're going to do is molecularly model iodine in our typical fashion, treating it as a spring. Instead of a harmonic oscillator like the green here, we're going to treat it as a Morse potential in a sense. And we're going to fit, or actually model, iodine at different internuclear separations R, and calculate the molecular energy of each individual internuclear separation. Then we can plot those and fit those with a Morse potential function, which is as follows here. dE is the distance from the bottom of the well to the dissociation energy, and note that A is equal to the square root of the spring constant divided by that depth of the well. So let's go through WebMO and see how we can implement a molecular model of iodine. So here is WebMO you're familiar with, and we're going to make one of the simplest molecules we can, a diatomic, but we need to have iodine. So I'm going to click on iodine from the periodic table, click, and draw a bond. Now we have I2. But we want to specify exactly the distance between the nuclei. So once we do this once, we can then start with the structure we built already, build again, and then edit the length of the bond. So let's do that. We'll go to Tools, we'll select Adjust, and then I'm going to click on one iodine and the other iodine. When I just made this by hand, it came out to be 2.899 angstroms. So let's go ahead and click the Adjust menu, and we will adjust the bond length, and let's just call it 4 angstroms. Apply, you can see it lengthened, and now here is our molecule. What we're going to do is now submit that for calculation, and the engine I'd like you to use is NWChem, and just choose first available server. And what I would suggest that you do is name the job something very useful. We're going to be using density functional theory, and we're going to make sure it says B3LYP, so I'm going to say dash B3LYP for the type of density functional, which we haven't talked about in class, but just enter it as I mentioned, and we'll talk about that later. So for right now, I'm going to just leave the basis set at whatever the default is, and we're going to see how we can actually add a basis set that will have functions that will be accessible for iodine. Now iodine has an atomic number of 53, and since we have 2 of those, we have 106 electrons to deal with. As we saw in lecture, dealing with 1 electron is possible. 2 gets very complicated. Imagine 106. So it's handy we have computer modeling to try to think about this. So what we need to do, most basis sets do not include iodine since it's such a large atom. So one convenient thing is you can go to the website called the EMSL Basis Set Exchange, and there are 601 published basis sets. And you can also choose which modeling system you're interested in using. We're going to use NWChem, and if you click on I for iodine, you notice that you have 104 published basis sets that include iodine in them. What I'm going to suggest you do is you use either the 6-311G or the G star. You can try to go with higher basis sets if you like, but I would run a test run first to make sure that it doesn't take over maybe 5 or 10 minutes with a 4-core CPU. So I'm just going to choose the 631G for right now. Make sure that the Optimize General Contractions button is checked. Don't worry about too much what that means. Click Get Basis Set, and what you see is a new window that'll pop up. And what you need to do is select. Let's move this in here a little bit easier so you can see. We're going to select this whole thing, so I'm going to click and drag. And note things that start with the pound sign are comment statements. And then this is actually the specification for all of the parts of the basis set. So I'm selecting that, and on the Mac I'm hitting Command C or Windows Control C to copy that. And so what we can do is go back to Northwest Chem. I'm going to tell it 6-311G, so I know what the basis set, and then I'm going to say, what did I choose for the length? I think 4.0 angstroms. So I have a record of that. And I'm not going to hit the continue button, but I'm going to go to advanced, click Cartesian coordinates, and then preview. Click the button generate. And notice right here, it says basis, no print, and then it says use from the library this basis set. We're going to replace that whole thing. So select starting with the basis all the way through end, and then paste over that this new basis set. So what the computer software will do is it won't use the one in its library, but it'll use the one we just got from the basis set exchange. So hit continue, and then you'll have to tell it, yes, we edited the file, but go ahead and do it anyway. So what we'll see is that you have this one running like we've been doing before. And as an example, here's one that I ran with a 5 angstrom distance. And when it loads, we will see a very long bond. So here is iodine with a 5 angstrom bond length. And if we go down a little bit, one of the values it calculated is the DFT energy. And what you want to do is copy that number, including the minus sign. That is in units of Hartrees. And you can look in our text to see how Hartrees relate to joules, etc. But just copy that number. And that number is going to go with that particular bond length. Let's just go back and check here in WebMO. Notice that the one I just ran is complete. That took very little time, so that basis set is not as complicated as others, but I wouldn't go with basis sets that give you a runtime of more than 5 or 10 minutes, because you're going to want to do many repetitions of this model. So if we go back into our one we just ran, since I couldn't remember what I set this at, let's check. So I'm going to click the arrow tool, and I'll click the 2 atoms. Try that again. Well, there we go. Well, that doesn't seem to be working, but I think you understand from the other example I did how to set up that bond. So at the end of that run, if you wanted to run another one, you would click on this, view it, and wait, and wait, and wait. Sorry, there's not much humor in this one. You would then click New Job for this geometry. Once it rebuilds, you would do Tools, Adjust, and then you would select the 2 bonds, or 2 atoms again, and then you want to change the bond length from whatever it was to the new value. If we said 5.0 angstroms, and say OK. Whoops, I didn't apply it. 5, and OK. I must have applied it. Anyway, so then you can keep repeating this process, and so what you'll do is end up with a collection of internuclear separations that'll give you energies that will change as a function of distances. So I've done that for an example, and if we go look at the data I got, I have data ranging from 2 angstroms up to 8 angstroms. And you can see this potential curve matches the kind that we saw for the Morse potential. In addition, we can fit these individual data points with the Morse curve potential. And I'll show you how to do that. So what you have to do is create a new function, and you would basically just click on New Function. I'm going to click Edit Function to show you what I've made. So in the Edit function, I have essentially put in the Morse potential, used just basic coefficients that have really no name. You can use whatever names you like, and then an independent variable. I've reproduced the Morse potential. Note I've added a constant because there'll be an offset from 0 just to have that be fittable. And once you've done that, you would hit Test Compile, and you would replace or save the curve. And note that I've already done this fitting on these. You will have to, when you fit this, have an initial guess. And so the way I arranged this, based on the heart trees I had for my infinite separation, which is around minus 13,839 heart trees, I put that in as an initial guess, and then I put 0.1 for the K2 parameter, 1, and then 2.9 for the equilibrium bond distance. So if I hit Do It, it did that fit, and it has fit the green one. This is a different basis set. This is the G311G star instead of the G11 just G. Notice there's a lower energy, like we talked about, in terms of optimizing the function of the basis sets. Okay, so your goal for 344, the molecular modeling, is to model iodine as a function of internuclear separation, and we'll be able to compare that with what you get from the data from the lab. Now keep in mind there's a Morse potential for the lower and the upper, the ground state and the excited state. We will probably only measure, or I should say model, the ground state. And again, I would go from roughly 2 to 8 with more model or more finely separated radii or separations around 2.9 or 3, so you can get the minimum, and then get out to the point of separation so that you no longer have an attractive force between the two atoms. That will do it. Thank you, folks.